systems more broadly, we need to focus on how foundation models provide key opportunities to accelerate the simulation tools. Now, the premise of this talk is that foundation models provide the key opportunities to accelerate the full AV development program. Here, by a foundation model, I mean a model that has been trained on broad data, typically at the intimate scale and in a self-supervised fashion, that can be then fine-tuned to a variety of different downstream use cases. Example of foundation models, of course, include large language models, vision language models, video generation models, and so on. Now, we're not quite yet at the level of one massive model that can ingest any data modality that can be downstream to any possible use case. But this idea of a pre-training on broad data and then fine-tuning on key use cases has proven useful in a variety of different contexts, as many of you, of course, are already aware. So now the question is, how do we access this generalist experience for the purposes of AV development? And the answer is in multiple ways. Foundation models provide opportunities to accelerate different elements of an AV development program, from offline processes, such as, for example, data auto-labeling or scenario generation or simulation, all the way to the onboard spec by enabling new architectures or improving existing, for example, driver assistance systems architectures. So the key point here is that the foundation models provide the opportunities to accelerate the full AV development cycle. In this talk, I will focus in particular on how foundation models provide opportunities to accelerate the simulation tools, and then I will discuss how these simulation tools, powerful simulation tools, can be used throughout the AV development program, from initial development all the way to validation. Now, in the past few years, neural audience fields, like, for example, nerves, have emerged as a very promising tool for scene representation and reconstruction. For example, here, our recent work, MRNerve, can decompose a scene into its static environment, dynamic components, as well as an optical scene flow, all in a self-supervised fashion without any input from humans. And with such a powerful representations, we can then resimulate such scenes in novel targeted ways, for example, in visual space, but also in point cloud space, where we can regenerate and reconstruct point clouds through which an AV can drive. Now, a caveat here is that all the agents on the road in this reconstructed environment are being replayed, so they do not react to what the ego vehicle under test is doing, which motivates, and this is related to the previous talk, the design of data-driven or non-data-driven behavior models. And this is a topic that my group has done a lot of research in, and over the years, we've been pushing the boundaries in terms of realism of the models, diversity of the models, and controllability of the models. Our latest work on this topic is represented by CAT-K, which is a novel fine-tuning methods for tokenized traffic models. So basically what CAT-K does is to strike a balance between open loop and closed loop training. The main idea is to roll out a policy through bias sampling so that the rollout stays close to the ground truth, which enables the use of the ground truth as a supervisory signal similar to traditional open loop imitation learning, thereby sidestepping the complications of closed loop training. We'll be presenting this work as an oral at this CVPR. Max Eagle will be giving a talk, so I will leave the details to him. Here, I will just say that through this supervising fine-tuning strategy, we can take a small 7 million parameter model and make it outperform a larger, much larger 100 million parameter models, to a point where our model actually topped the leaderboard for the Waymo OpenSim Agent Challenge in 2024. So this is quite promising, and we're also productizing it as part of the NVIDIA simulation overall offering. So now this is great. We have a strong capability to generate behaviors for humans, like bikers in the scenes, or pedestrians, or other drivers. But generating scenarios that really stress test a system and allow you to improve a driving policy is quite difficult. It requires essentially artists and designers that really craft a scenario that it's useful for training and testing purposes. And here, this is an area where foundation models can really help. We have explored how large language models can provide an interface to translate specification of what type of scenario we want into the realization of that scenario. In particular, we have a couple of works along this direction called LCT-Gen and ProC. The idea is to ingest the description of a desired scenario through a large language models and turn that description into a structured representation. The structured representation, in turn, is fed into as an input into a map retrieval framework that extracts a plausible map for a set of possible maps, as well as into a motion generation that generates motions for the next few seconds. So the reason why this tool is quite useful is that we can use as a conditioning information any textual source of information. For example, police crash reports. That's exactly what we did. We took all the police reports that have been recorded in the United States, passed them through this scenario generation model, and then re-rendered them and used them as a source for stress testing scenario generation. This is important because it's relatively easy to generate adversarial scenarios. But generate scenarios that are actually plausible can happen in real life is very nuanced and difficult. Grounding the scenario generation capability into crashes that have actually happened gives us at least some feeling that these scenarios could indeed be plausible. Okay, so with these powerful tools at hand in terms of scenario reconstruction and targeted scenario generation through large language models, we can do pretty cool things. For example, here, let's assume that you want to generate a scenario whereby a driver is inattentive, in the sense that he's not stopping at a stop sign. On the top row, I'm showing you a video that has been recorded in real life, whereby the gray vehicle is indeed stopping the stop sign, is doing the right thing. Now, through our tool, what we say is we want to generate a similar scenario where the same vehicle does not pay attention to the stop sign and just drive through the intersection. And that is exactly the output of our tool in the bottom row. The simulation should be choppy here. You saw how the tool it's a bit messed up. What you would see is that the tool will remove the gray vehicle and reinserted it into the reconstructed scene that is purely simulated, and the vehicle will zip through the intersection. So just imagine it. It's a simulation workshop at the end of the day, right? Okay, so all of this is great, but there is one caveat. So reconstruction pipelines, such as NERFs or Gaussian plotting, they do reconstruct. So essentially, you need to have recorded a given scenario in order to reconstruct it with some minor variations in simulation. And this actually poses a problem because at some point this reconstruction pipeline might break down if you have a variation with respect to the recorded drive that is too extensive, and you cannot really generate completely new scenarios. So for example, here I'm showing what happens with an in-house neural-based simulator that actually Jean has been one of the key developers. You see that as the vehicle is making a U-turn, the neural reconstruction methodology breaks down, and you see a mess of holes and artifacts. It's actually a minor miracle that the policy can still drive in such fully reconstructed scene. So one thing that is intuitive then is we are living in an era of video generation models. So why don't we use video generation, like for example, the Sora model or the Cosmos model from NVIDIA to generate new scenes? Well, here I'm showing a video that is produced by a Cosmos video generation model. This is very promising, but one of the issues is that these models tend to hallucinate. And so the question is, how can we somehow bring together the best of both worlds, the physical accuracy of neural reconstruction methods with the generation capabilities of video generation models? That's exactly what we do with the recent work we presented at ICRA called Dream Drive. What the idea is to, as I said, bring together video generation capabilities with neural reconstruction capabilities. The idea is very simple. So essentially, we start from one image of the word. We use that as a conditioning input for the video generation model pipeline, and we generate a video of a scene through which the vehicle drives. You can see here some inconsistency. For example, the grass on the top right changes colors a bit arbitrarily between green and brown, which doesn't make much sense. It could be actually problematic for training because a policy might actually latch on to such an artifact. Then we pass this video through a 4D reconstruction pipeline from one of the pipeline we developed, actually Storm, and then we can place a vehicle that drives through this 4D reconstructed world. So it's a fairly simple pipeline, but in this way we ensure plausibility and realism in two ways. First, because we ground the generations with an image, but that's the trivial part, but most importantly, because we reconstruct the entire scene through a 4D representation that ensures geometric consistency. All right, so this again looks very promising, particularly for the purposes of testing stacks or training stacks. But my next question is, can we use simulation even for validating stacks? So in general, one important role for simulation would be that of accelerating the safety assessment of an AV stack. Indeed, NVIDIA is investing heavily on physical AI safety through a program called NVIDIA Halos that was announced at GTC in March by the NVIDIA CEO, Jensen Huang. And NVIDIA Halos actually brings under the same umbrella a number of research results from a group on the topic of AI safety. But back to the topic of validation, can we use simulation for validation purposes? Here, the point that I want to make is that this use case is a bit different from training and testing. For training and testing, you're typically interested in directional information, whether a new policy that you have synthesized is better than a previous policy. The specific numbers related to the metrics are not that important. For validation instead, you really care about the absolute number related to a metric. What is, for example, the time to collision for a given policy? So, as discussed, there have been a lot of advances in the field of simulation. So can we make this simulation so realistic that we can actually trust that absolute value of performance? Well, that's a tricky question because, first of all, that entails that you need to use real data to validate your simulator, which is hard. But second of all, when you have a new policy, that policy might actually depend on different inputs than the previous policy, which puts into question whether the previous validation process for the simulator applies to the new policy as well, which means that you have to constantly revalidate your simulator, which defeats the purpose of actually using simulation. So a more pragmatic question that we've been answering is whether we can pair real-world tests with the simulation data to make validation more data efficient. Specifically, we do that through the lens of variance reduction techniques. What do I mean by that? Of course, there are different axes to validate a system, but for the purposes of this talk, let's assume that what we want to estimate is the average of a given metric f, where f is your desired metric. The simple Monte Carlo estimate of this metric f is the arithmetic average over the different real-world trials that are used in order to get an episodic estimate of that random variable f, where n is the number of real-world tests. Now, the variance of this estimator depends on the variance of the random variable f, which we do not control, and the number of real-world trials that we use to estimate that random variable f, which we do control. Of course, the more real-world tests we have, the better the estimation of random variable f is. Now, the question is, can we use a control variate in order to reduce the number of samples n that we need? By control variant, I mean a correlated signal, a signal that is correlated to the random variable we want to estimate, f, whose expectation is known. And the idea of estimating through a controlled variate scheme is to estimate the random variable f as the difference between the random variable f and the control variable G, so the correlated signal G, to which then we add back the expected value of G to correct the result. Note that if you take the average of that first equation, you still get the expectation of F. So why do we do that? So in general, estimating differences is much less noisy. Intuitively, if F and G are correlated, then when we take the inference, when we take the difference, the noise cancels out. And so the difference is a less noisy signal. In practice, if you do a little bit of math, you will see that the variance of such estimator is the same variance we had before, multiplied by 1 minus rho squared, where rho is the correlation between random variables F and G. Of course, if rho is very correlated, then for the same level of confidence, you would need much fewer samples. So then the idea is pretty simple. Why don't we use a simulation as our control variant? But there is a catch. We don't know the expectation of G. We don't know the expectation of the metric in the simulation environment. But this is fairly simple to address. We can just use simulation-only measurements to estimate the expectation of the control variant G, with the idea that simulation-only measurements are very easy to acquire. So let's say that we use K simulation-only samples to measure the expectation of G. Then the variance for this new estimator is very similar to before, with the exception that now the coefficient of correlation is multiplied by K over K plus N, where again, K is the number of simulation-only samples, and N is the number of a pair real-world and simulation samples. As the number of simulation-only samples goes to infinity, we get to the previous result. So how does it work in practice? So let's assume that we want to estimate the average distance to the nearest obstacle for a given policy as a proxy for a collision avoidance metric. So what we do is to pair real-world samples with the reconstructed samples. The real-world sample is on the left, the reconstructed sample is on the right, and we drive the same policy, of course, in both real world and C. In this case, the correlation between the two is about 0.8. By leveraging inexpensive sim samples, we can then achieve equivalent confidence level as using 4x the number of expensive real world samples. And actually, we're using these technologies to reduce by order of magnitudes the amount of real world samples that we need in order to simulate a given metric. Now, in this case, simulation and real world were very much correlated. So what if the correlation signal is weak? Well, in that case, you can either improve the simulator, sure, but what you can also do is to learn a metric correlator function that maps your weak signal and some features of a given scenario into a new refined surrogate signal and use that as your control variant. And we show that in the case, we can still obtain significant gains in terms of how many samples we need, or samples we need for the given confidence level. So quite excited about this work because it's one of the first ones that addresses the topic of using simulation for validation with the statistical guarantees. Now, one last thought before concluding. So both testing and validation, of course, help with the revealing performance gaps. Like considering this case a manipulation setting, for example, testing can reveal issue with tying a knot or issues with tucking a box beneath a table or issues with grabbing a book, in this case, the robotic arm, dropping a book while taking another book. Now, the problem is once we identify these issues, how can we systematically identify the root causes of these issues so that we can retrain the model and hopefully improve the model? So this is a tricky question because, of course, with a fully data-driven policy, we don't have a control logic that we can simply modify. So the question is, how do we relate test time behavior to the quality composition of the training data? For example, in the training data, we might have demonstrations with mixed skills. Some humans may be better than others, and we want to, of course, remove poor demonstrations. We might have fragile behaviors. We might have spurious correlations. So how do we identify the data in a very large and diverse data set so that we can retrain the policy and then improve the policy. And to ground this question in something more concrete, let's assume that our training pipelines is a standard and widely used behavior cloning pipeline. So the question then is, as I said before, how do we relate closed loop performance to individual samples in our training data set? Our key insight is to turn the problem into a counterfactual reasoning problem, whereby we try to reason in terms of the inclusion or exclusion of data and how that impacts closed loop performance. Essentially, we want to answer the question, what happens if we remove a given trajectory tau from the training data set on closed loop performance? For that, we turn to a robust statistics methodology referred to as influence functions. Influence functions are not a new tool. They were developed in the 1970s, and they were popularized in the machine learning community by a seminal paper by Ko and Yang in 2017. And since then have formed basically foundations for interpretability research in deep learning. And the idea of influence functions is to reason about the sensitivity of closed loop performance with respect to reweighting the importance of one of the samples. So essentially what we do is to take the original behavior cloning objective, and then we upsample one of the trajectories by a quantity epsilon. And then we want to compute the change in expected return with respect to an infinitesimal upweighting of the importance weight epsilon. Essentially, the derivative of the return j with respect to the upweighting epsilon. That's basically the sensitivity with respect to an individual data point. Now, this is difficult to compute, unfortunately. First of all, different from the traditional use of influence function in machine learning, we are interested in not just attributing a data point to a given performance task, but to a sequence of decisions that are computed in closed loop. And we don't know the environment dynamics, so that's difficult to compute. So our main contribution is to show that we can use policy gradient tricks to decompose these complicated derivatives into an empirical estimations of our policy rollouts, whereby for each episode, what we compute is the influence of a given trajectory on the trajectory, on the action log likelihood. And this is something we compute by reusing previous tools. So the analysis is a bit complicated, but the main point here is that we can estimate these derivatives just by taking an average of rollouts by using fairly standard policy gradient tricks. So in this way, we can then rank the different data points in the data lake through this influence score. And with that information in hand, then we can use that information to either remove samples from the training set or decide which new samples we want to add to the training set. And we show that with this relatively simple pipeline, I would say, we can dramatically improve the performance of a state-of-the-art, for example, diffusion policies. The method is called Cupid, the god of love. The title of the paper is Curating Data Your Robot Loves. Was very excited about this acronym and very proud of my students. And then I found out that actually the acronym was provided by ChatGPT. But anyways, I still like the acronym. So as you can see, with Cupid, we can improve quite significantly the performance of a base diffusion policy, the one in gray, or a policy that is curated but just randomly pruning the data set. By essentially moving all the previous bad behaviors we saw in terms of making manipulation of objects more robust, removing spurious correlations, and so on and so forth. I mean, the main takeaway here is that in an increasingly more data-driven world, we should view data essentially as an optimization parameter we want to optimize over, and influence function appear as a promising tool to this purpose. So it's time to wrap up. A few takeaways. So the first one is that foundation models provide opportunity a data cast in the context of the onboard stack that actually provide significant opportunities to accelerate everything that is required to be the robot, including, of course, its In the context of a simulation specifically, multimodal large language models and visual language models and video generation models can help in multiple ways, from enabling controlled scenario generation, for example, through the work LCTG, all the way to realizing highly unusual corner cases, for example, leveraging techniques from video foundation models. So far, simulation has been predominantly used for the purposes of testing and training, but I think simulation is now ripe also for the purpose of validation. And simulation doesn't need to be perfect to enable validation. As I discussed in this talk, a more pragmatic approach entails understanding how to best mix real and simulation data through the lens of variable reduction techniques. And finally, as I just said, the training should increasingly view basically as parameters to be optimized, and the influence function appear to be a promising paradigm for this task. So with that, I'll stop it here, and I'll be happy to answer any questions.